Module 1 Mastery Assignment by Leslie Oy. Topic 1. Partial Fractions. When integrating a fraction, sometimes we can split the denominator through partial fraction decomposition. This is the process of breaking up a fraction to express it as the sum or difference of multiple fractions. Through partial fraction decomposition, we can then integrate partial fractions by using natural log integration rules. However, there are some things we need to keep in mind. For instance, when the numerator has the same or higher degree than the denominator, we need to do long division before decomposing a fraction. Also, for AP Calculus BC, we will only decompose fractions when the denominator can be factored into non-repeating linear factors. This means we won't work with repeated factors and/or quadratic factors. Here are some steps for partial fraction integration. First, factor the denominator of the original integrand. Then, rewrite the integral as a sum of multiple fractions, each having a denominator equal to a factor of the original function. Third, solve for the coefficients of each of the decomposed fractions. Then, rewrite the integral as separate integrals of fractions with linear denominators. Fifth step is factor out the coefficients of the integrand in front of the integral sign. Then, integrate each component using natural logarithms. Don't forget the plus c. And finally, use the properties of logs to combine the integral into one logarithm. Now that we know these things, let's look at an example. Integrate the following fraction, x squared over x squared plus 3x plus 2 dx. Since the numerator has the same degree as the denominator, we first have to do polynomial long division. So this is how we are going to set it up. Notice I put in zeros for my constants. Now we have to see how many times x squared goes into x squared, and that is once. So now we can multiply it. So x squared plus 3x plus 2. And remember, this all has to be subtracted, so we put a negative sign out front. And when we do this, we're going to get negative 3x minus 2, and this is our remainder. So now we can rewrite this as the integral of 1 plus the fraction negative 3x minus 2 over x squared plus 3x plus 2 dx. So now we can factor out the negative and get the integral of 1 minus a fraction of 3x plus 2 over x squared plus 3x plus 2 dx. We can now perform partial fraction decomposition on the second part of the integral. First, we need to factor the denominator. So when we do that, we get 3x plus 2 over x plus 2 times x plus 1. Now we can rewrite this as a sum of multiple fractions. So we're going to get a over x plus 2 plus b over x plus 1. However, we now need to multiply whatever is missing from their denominators. So we will get a times x plus 1 all over x plus 2 times x plus 1 plus the fraction b times x plus 2 all over x plus 2 times x plus 1. Now that all of our denominators are the same, we can focus on the numerators. Now we can solve for the coefficients a and b, and we're going to use their zeros. So when we have x equals negative 1, we're going to get 3 times negative 1 plus 2, and the a cancels out, equals b times negative 1 plus 2. And when we do this, we're going to get b equals negative 1. Then we can do the 0 x equals negative 2, and when we do this, we're going to get 3 times negative 2 plus 2 equals a times negative 2 plus 1, and the b cancels it out. We're going to get negative 4 equals negative a, and that means a equals 4. We can now substitute the values of our coefficients into our original integral. When we substitute the values a equals 4 and b equals negative 1 into our partial fraction decomposition, we're going to get the integral of 1 minus, in parentheses, 4 over x plus 2 minus 1 over x plus 1 dx. When we do this, we can separate our integrals. So we're going to get the integral of 1 dx minus the integral of 4 over x plus 2 dx plus the integral of 1 over x plus 1 dx. Notice I had distributed the negative from earlier, so we can draw out the coefficients at this point, so we're going to get the integral of 1 dx minus 4 times the integral of 1 over x plus 2 dx plus the integral of 1 over x plus 1 dx. And when we use our natural log rules for integration, we get x minus 4 ln of the absolute value of x plus 2 plus ln of the absolute value of x plus 1 plus our constant of integration. We can finally combine all of this into one natural log, and we're going to get x minus the natural log of the absolute value of x plus 2 to the 4th power all over x plus 1 plus c. Topic 2. Integration by parts. Integration by parts is a technique used to integrate the product of two functions. This is based around the product rule. There are also some other key terms we should know, such as integrand, which is the expression that is to be integrated, limits of integration, which are domain values that bound the integral, and product rule, which is the method for differentiating the product of two or more functions, and here it is below. The product rule helps us derive the formula for integration by parts. If we integrate both sides of the equation, we're going to get uv equals the integral of the derivative of u times v dx plus the integral of u times the derivative of v dx. The integral I've highlighted is the one we want to solve for, so if we subtract the integral of the derivative of u times v dx from both sides, we're going to get the following. And you can see how this equals uv minus the integral of v du. Here are some tips for choosing u and dv. When you choose dv, make sure you can find v, so make sure dv is relatively easy to integrate. It is also helpful to have u differentiate into something simpler. So here's a helpful mnemonic device we can use to help find u. As you can see, ILATE prioritizes more complex functions. Now that we know these things, let's look at an example. Integrate x squared times sine of 4x dx. First we need to identify our u and dv. X squared will be u and sine of 4x dx will be dv. So du will be 2x and v will be negative 1/4 cosine 4x. So now we can plug it into the formula uv minus the integral of v du. We get negative 1/4 x squared cosine 4x minus the integral of negative 1/4 cosine 4x times 2x dx. We can simplify this and we'll get negative 1/4 x squared times cosine 4x plus 1/2 of the integral x cosine 4x dx. Now we have to do a second iteration of integration by parts. So u equals x and dv equals cosine 4x dx. So du equals dx and v equals 1/4 sine 4x. Now we've plugged it again into the formula uv minus the integral of v du. After a few steps, we will get negative 1/4 x squared cosine 4x plus 1/8 x sine 4x plus 1/32 cosine 4x plus c. However, there is an alternate method if we're running low on time. This is the tabular method. First, we make a table with two columns, u and dv. Then we take the derivatives until we get 0 in the u column. Integrate the same number of times in the dv column, then draw diagonals from the first u to the second dv, and then so forth. Then we alternate signs, positive, negative, and don't forget plus c. Let's go back to our example. If we set this up with u equal x squared and dv equal to sine of 4x, first we're going to differentiate u all the way to 0. So it's going to be 2x, then 2, and then finally 0. So we're doing this 3 times. So we're going to do the same number of integrations on the dv side. Then we will draw our diagonals and then add our alternate signs, positive, negative, positive. So now we can go straight to our answer by multiplying the terms connected by diagonals together and indicating if it's being subtracted or added. So our final answer is negative 1/4 x squared cosine 4x plus 1/8 x sine 4x plus 132 cosine 4x plus c. Notice this is the same answer we got earlier, but a much simpler method. We can do this when we have 2 or more iterations. This method is helpful for organizing our work and letting us check to make sure we distributed our negatives correctly.